All right, well, I want to thank everyone for coming out tonight in the pretty cold New York evening. Welcome you all here. We have with us today an exceptional speaker of the evening. I'll be back. Anyway, with us tonight we have someone very exceptional. He is the co-founder and CTO of Tengen. Hello. Co-founder and CTO of Tengen, which is, for those who aren't aware, the MongoDB company. He is one of the core contributors to MongoDB and has single-handedly built quite a big portion of it, I would say, at the end. Is that accurate? And prior to this, he was also the chief scientist of ShopWiki. And we have with us, without further ado, Eliot Horowitz.
Usually I wouldn't use a mic for this, but I'm recovering from the cold, so it'll be a little hard for me to speak without a mic today. So first, thanks for having me. I'm Eliot Horowitz. I'm the CTO of Tengen. I'm the CTO of Tengen before there was a Tengen, so that's very exciting. And as Eric said, I did a lot of research at Brown long ago. After Brown, I was at DoubleClick. How many people here know DoubleClick? Anyone work at DoubleClick here? Wow, usually there's a few. So that's me. So I think Eric already asked this. So actually, first two things. One, if anyone wants a copy of the book, it's online, as Francesca said. And also there are 7,000 copies of the Tengen office. So if you can find it when the office hours are, we literally have 7,000 of them. I would love to get rid of it. So come on by. So let's talk a little bit about why we started building Mongo. We started building Mongo about 4.5 years ago. Basically, the end of 2007 when we started building Mongo. So what did we care about? Why were we doing this at all? So one is for horizontal scaling. Right? You think about DoubleClick, so it's an ad serving company. Bought by Google a few years ago. DoubleClick serves 20 billion ads per day. It's a lot of ads per second. It's 1,000 ads per second. So that's a lot of scale. ShopWiki was crawling every single store on the internet and downloading every single page and extracting content from them. And so it's crawling hundreds of millions of pages every single day. Lots of scale, lots of challenges there. Storing billions of images. And all these scaling problems ended up being, in the end, the problem was always databases. Right? Scaling app service is easy. Think like a crawling system. Scaling the number of machines downloading content from the web, that's easy. Just add more crawlers. Adding more web servers is easy. Just add more web servers. The problem is being how do you store the data? How do you make that all work? It's not working. So, how much better? The problem was always going to be the database, right? Scaling app servers is you always crazy. Yes. On the scale, alright, so the problem ends up always being the database, right? Where do you put the data? How do you query it? How do you make that scale, right? When all of your data can fit in one machine, it's really easy. When you can just buy a bigger machine, you just buy a bigger machine and spend more money. There are problems with that at some point, right? You've got it, you hit a wall, whether it's how much money you can spend on a physical box, or maybe it's how the largest size box Amazon has, AWS has to offer. Maybe it's the largest size box that someone like Scale or whatever hosting company you're using has to offer. And maybe it's just that you don't want to spend $2 million in a single box and hope to hell that it doesn't crash. So you want to actually distribute your data and figure out how to scale it. So that's a big problem. Two is that things are much more real time than they were you think about when relational databases were really designed, came of age, just 30, 40 years ago, things were very different then. Think about a company like DoubleClick. DoubleClick now is 24/7. It's a big deal. 20 billion nets a day. If it goes down, it's a big problem, right? So DoubleClick was first created in 1995 or 1996. It first started really big production in 1996. Every Saturday for 3 morning, every Saturday for 3 hours in the morning, there's a maintenance window. During that maintenance window, ads were still being served, but no one could edit their ad. No one could actually edit their ads. People who were working with the ads couldn't do anything. The reason for this was all database maintenance, right? So, like 3 a.m. to 6 a.m. Saturday mornings, there was database maintenance window, and this was there for many years, and for a long time it wasn't a problem. And then a few things changed. One is that things became much more international. So for people who were instead of 3 a.m. it was 3 p.m. for them, that wasn't really an option anymore. They didn't like that very much. And when people actually started working 24/7, and the thing with the web now, if Facebook was down from 3 a.m. to 6 a.m. every Saturday morning, people wouldn't be so happy. And this was a change. Right? 15, 20 years ago, if things were down on Saturday mornings, no one actually cared very much. Right? Banks closed at 6 p.m., 3 p.m. And so you couldn't access your bank account information in the middle of the night anyway. So if they wanted to work on a database, they took it down and did work on it in the middle of the night. And this was standard for a very long time. And when the internet really came of age, this no longer became an option. Maintenance windows went away. Sites that have maintenance windows now are kind of laughed at. And that's a big change. So that means your database has to adapt in real time. You have to be able to make changes to it in real time. You have to be able to do all the maintenance that you want to do in real time without taking it down. And that's a pretty big theoretical change for a lot of things. 2 is that, 3 I guess. Development time has gotten compressed a lot for many reasons. Programming languages are much more productive. People are programming in Ruby or Python or Java, not Fortran and COBOL anymore. So people tend to be more productive in Python than they were in COBOL. Right? You can build more applications, which means that development time is faster, which means you want the database to not be the bottleneck in your application development time. You want to be able to do much more iterative things. When you're developing software that you're going to shrink wrap and sell in Walmart, a 1-year release cycle makes a lot of sense. When you're on the web, it's hourly. How many people here work on hourly release cycles? Or at least daily release cycles? Weekly release cycles? A lot of old-fashioned monthly release cycles? How many people here deploy websites? All right, so that's what, okay, fair enough. So with the people deploying websites, there's a large tendency to deploying, it's not hourly, daily, or at the very least weekly, or certainly not monthly or bi-monthly. So people have to be able to develop faster, to adjust quicker. So that's a pretty big change. 2 is that, if you think about, So 4, if you think about, starting websites now, one of the big things people like now is that, hey, I can go and build a website, it gets to be launched without spending any upfront money, right? When a website wanted to launch in 1999, they went out, raised $20 million, spent $5 million buying some hardware, and that's how they launched. Now you can go put a credit card into Amazon, and you can be up and running for about $3 a month or something ridiculous. Probably even for free, it's free to you. Right? So the whole cost of entry is much lower, and you want that to go through your whole stack, right? You're using open source development tools, you're on a pay-as-you-go service like Amazon, and you want your database to be free too. And not only do you want it to be free, but you want it to be free to start and then scale up as you go so that you don't have to rewrite everything and rebuild your entire application once you get a little bit of traffic. So those are some of the major changes. And if you think about some other things that have changed, right? What were computers like 30 years ago compared to what they are today? Right? The amount of RAM I have on the amount of memory I have on my phone is computers had 20 years ago. Somewhere I have a chart that describes it more accurately, but these have changed a lot in the last 30 years of computers. So databases, in many ways, really needed to change. So what is NoSQL? How many people here like the term NoSQL? Okay, that's good. So what is NoSQL? So NoSQL really is this term. It kind of happened by accident before anyone realized it was smart enough to change it. No one really knows. At least I don't know where it came from. I feel like I should know anyone. But basically, it's a collection of a whole bunch of different things that are all very different. There's only a few things that are common, and those are temporary at best. Right? They're all non-relational, though there are some things that are kind of relational that are kind of sneaking in there also that make sense to sneak in there. There are no joins, sort of. Some of them have joins, some of them will have joins. There are things that are like joins, but they aren't joins in the traditional sense. None of them use SQL today. Some of them are starting to move that way. Some of them are doing things that are kind of hybrids of SQL and not SQL. So there's lots of things that are like that. So really, it's just different data. It's really just new databases, right? And they have these somewhat commonalities, but in 5 to 10 years, I'm not sure how you'll be able to define them. And I don't think SQL, I certainly don't think whether or not they support SQL or not is really defined. So where do these things come from, right? So one, how many people here have used object databases in the 90s? I think you're both. So object databases were popular for about 3 days. And they were widely used for 3 days. A friend of mine actually was one of the founders of one of them. And he said they were popular for about 2 hours, but he's a pessimist. And basically the idea of an object database is, right, if you're programming in C++, you take a C++ object, you can store it in a database, and you can do things with it. And there are lots of good things about them, and there's a lot of research done. There's a lot of problems too. But, so that was pretty popular, and they died off pretty quickly. So that didn't work. So how did people start scaling 15 years ago? Mostly with the application layer, right? How many people here have done built a partitioning system in the application layer to scale across many instances of a relational database? It's like 6 or 7. Right? The idea is pretty simple, right? You've got an application, and your data no longer fits on a single database. So what do? You say, all right, I've got 1 billion users, and every user whose email address starts with A through E, goes to this server, email address starts with F through M, goes to that server. And you do that, right? I built these systems myself. They're kind of a pain in the neck to manage. Everyone I know who's building large systems, and 10 years ago, this is what they were doing. Like, they were just manually building systems. We wrote a lot of code, we make it work, we hacked this together. It was kind of a mess. Right? Google themselves did this internally a lot too, right? AdWords was built entirely with MySQL, and they kept, they had their own custom partitioning system on top of MySQL and scaled it, to 32 to 4. I have no idea how many MySQL servers are running out now, or if it's on MySQL, but they handle this all themselves. And then the next thing that came about was distributed key value stores. Right? Distributed key value stores are basically databases that the only operations we do in them are get and put. Right? So think like a memcache interface where you can say, hey, I've got this key, I've got this data, put this data at this key, and get me this thing. And these things were one of the first kinds of distributed databases because they are sort of the simplest kind of database you can have. Right? It's basically a distributed hash table. And so for certain use cases, they work really well. You need that, and they're very easy to, you basically strip down all the features, as many features as you possibly can to get something useful that is useful for certain use cases where you need to scale it. And if you design your application or you use it as sort of a very specific purpose, you can get a pretty scalable database pretty easily. So these got, people started using these, and then, people started trying to generalize this, right? So there are some big companies who were doing these things, who were getting frustrated, right? So Google created this thing internally called BigTable. BigTable is a distributed, a real distributed database. In some ways, it's more of a distributed key value store, but it basically allows them to scale databases very large, and they use it for a lot of their stuff internally. They wrote a paper on it called BigTable about a decade ago. That's very well read. Yahoo themselves has lots of these systems, and Yahoo wrote this paper called Peanuts based on the systems they have internally. And Peanuts actually, so BigTable is interesting because BigTable is actually a completely homegrown solution that Google built. It's all custom code, it's a whole new database. Peanuts is very different. Peanuts is basically a system that Yahoo built that sits on top of MySQL. So they have this very complicated layer on top of MySQL so that their code interacts with their system and their system talks to MySQL in the back end. But the back end is entirely MySQL, but they've made it such that they can distribute it and scale that pretty well. And those two are closed source, and very proprietary to Google and Yahoo. Then you've got Amazon. Amazon created a thing called Dynamo. Dynamo is system for doing an eventually consistent key value store, distributed key value store. Right, so the idea there is it's a key value store where you do get and put operations, and it's eventually consistent because Amazon built it with a very specific need in mind for their shopping cart, which is that what I really care about is that, what does Amazon care most about? Well, if you want to put something in your shopping cart, no matter what, you can put it in there, and if you put something in there 5 minutes apart, but you don't see it right away, it's okay, because what it really matters is when you go to check out, everything's in your shopping cart. Right? There's some weird things about Amazon that you say, hey, when I put something in my shopping cart, all I care about is that it eventually gets to my shopping cart. And they built this thing called Dynamo to support that. And there's a couple of open source implementations of it now, Sandra and React are the big ones, and I don't know how many people have heard of this. Amazon just released a Dynamo service yesterday, which basically is what they, basically a service on AWS for what they were doing themselves. So again, distributed key value store, useful in certain situations, but not really a generic purpose database. There's a few more, Medbase, Neo4j, spending too much time on this, CouchDB. So there's a bunch of other things in the space. So what did we really want to, and this has all happened a little bit before we started MongoDB and a lot after. But what did we really want to do with MongoDB, right? We weren't really happy with any of the choices out there. We weren't happy with what we had to do in order to scale things. So what really did we want? So let's just go through a little bit about what we were thinking about when we were designing Mongo, right? So this is basically conversations that we had roughly 4.5 years ago. And by the way, not all of these things are things that we've succeeded on so far. Hopefully we'll get there, but these are definitely sort of the root goals of what we're trying to do. If you have any questions, just interrupt me. That'll give me a break from speaking too, which would be good for me. So it's really fine. Yeah. So one is rich data models, right? Relational databases are, well, how many people here have used a relational database? Good. So I'm not going to say what a relational database is. But the way I describe it to people who don't know is there's basically like an Excel spreadsheet, right? Just like a very big Excel spreadsheet that you can write programs against. If you can model your data very well in an Excel spreadsheet, then a relational database works pretty well. Now, where does that break down? Let's say I want to store user profiles for my website in a relational database in Excel. Right? So I've got one sheet that has my username, my first name, my last name, my email address, my date of birth. That's great. Now I've got a bunch of addresses. I've got 3 addresses that I have this for myself: my home, my work, and I've only got 2 addresses. I've got 2 addresses. So how do I store that in my Excel spreadsheet? I've got 2 options, right? One is I can have address 1, I can have state 1, state 2, and just have more columns, right? And that works well if I only have 2, 1 or 2 or 3. But if I want to have n, if I want to allow someone to have any number of addresses, that doesn't work very well. The other option is I have a second sheet. The second sheet is a list of all the addresses, and I link them with some key. Right? Every person in my first sheet, every row has a ID number on the left. Right? So it's got a row number, and I can just link that and say, hey, I've got my second sheet that says, hey, this address is associated with this row. And if I want to find all the addresses associated with the person, I say, I go to the person, find their ID, then go to the second sheet, and find all the rows of that ID. Right? And relational databases basically do that. And SQL allows you to express those kinds of things nicely. So I would not say that's very elegant for storing user profiles, right? Because you've got to actually do this thing and go from one sheet to another. Right? You might call it joy. And that's what you do. And so that works very well for financial information and lots of types of information that fits well into Excel. What if it doesn't? Well, what you really want to do is do the same thing that programming languages did. Right? Programming languages create these things called objects. Right? Objects are nice because they allow you to store rich data and same things and put things together and combine user profiles and have lists and documents and have a rich thing that you can pass around that has everything associated with a person. And so why not store that in the database the same way? Why not say, hey, I've got my user profile thing that has my name, my addresses, a list of addresses, a list of likes, a list of dislikes, a list of dislikes, and take that and store it as a single thing in my database. That's kind of handy, right? So with relational databases, people actually started doing that. But the problem is they started saying, hey, I've got this blob that is my document, and just shove it into the database. But then you've got this problem of, well, I can't query it, I can't modify it atomically. I've got to I actually just got to load the whole thing and write the whole thing back. If I just want to actually query on an address, I'm going to find everyone who lives in New York. I can't do that anymore. So you kind of lose all the features of the relational databases that you actually care about. Right? Now you're using your relational database like a key value store without the benefits of the key value store. Right? It's not scalable, and you can't actually do anything with queries on it. So now that's kind of unfortunate. And so what we really wanted to do is build something that allowed you to store data in the same way you access it in your programming language, store that in the database, but still have all the power you're used to with SQL. Right? I want to be able to store a document in my database that has a user profile with a list of addresses, where each address has attributes like state, and it goes to find everyone who lives in New York and who is older than 30. That's a query I want to be able to run on my database, and I want that to work nicely. That's goal number one. Part of that goal was one, these things should interact very nicely with my programming language. But if I'm writing in Python, I'm using classes, maybe I've got a dict, maybe I've got these things. I just want to take that document and throw that in the database. I want that to work really easily. That's really important. Two is, data models change a lot, right? I add attributes all the time. I add features to my application all the time. And I want to be able to add fields whenever I want to. That's really important. And two, by the way, all these joins can be very costly because if I add attributes at different times, they can maybe in different places on disk, and there are systems that can keep things localized on disk by key. So this gets much more complicated. It's much easier if I can just say, hey, I've got this document, it's one thing, put it on disk together, so that when I want to load my user profile, I have to do a single seek on disk, read however big this thing is, and return to the user, right? I don't want to have to go bouncing around through different rows. I just want to go to a single place, load my data, shoot it back to the user, and be done. That's sort of what you want to do. Any questions on this? No? Good. So two, a question over.
How is it different than a denormalized relational database?
How is it different than a denormalized relational database? So how would you denormalize a user profile that has first name, last name, username, email address, and 3 addresses? Okay,
so it's the variable number of columns then?
The variable number of columns is the big one. I think depth is another one. But the biggest things tend to be arrays. That if you just have embedded fields, if you just have sub-objects to organize things, you could mimic that in a relational database. But if you've got arbitrary field names, so let's go back for a second. So there's a couple things. One is variable level. So anytime you've got an array of things, it's an array of addresses, it's an array of likes, an array of dislikes, an array of friends, any kind of data like that is hard to do in a relational database with joins. Two is, let's say you've got different types of things that are similar. So a big client of ours stores media. And they have images, they have videos, they have music, they have all these sorts of media that they're storing in Mongo. And the media has certain attributes, right? So you could have, let's say you have a folder. So you can have a folder that has music and videos. Or maybe this one has images and videos in it. So you want to have a collection that has certain key core attributes. So file name, upload date, creation date, owner, and also optional attributes. Optional attributes may be attributes of movies, like length, encoding type. Images may have different attributes, right? All the EXIF data, that kind of stuff. So if you want to look for different types of data in the same collection and make that work really well, that's really what to do in a relational database. If you take this to the extreme, let's say you're building, and this is something that I did myself at Shopwiki, is let's say you're building a product catalog, right? So let's say you're trying to build, take the Amazon product catalog. I can't remember the exact numbers, but these are pretty close. So at Shopwiki, we had about 150,000 different type of attributes a product in the world could have, right? Digital cameras have a certain set, right? Optical zoom, digital zoom. Clothing has a different set, size, material. So if you look at all the different kinds of products you can find in the world, about 100 to 150,000 different types of attributes. Any individual product, on average, has 30. In a relational database, there's 2 ways to model this. One is you normalize it, right? So you have one table that has your 3 or 4 core attributes about a product, right? Name, image, price, that kind of stuff. And then a separate table that has product ID, feature ID, value. right? So if you want to load it in, that's pretty standard. The other way is back to the blob model, where you have one table, but you store all the features in one blob, in one big column. So in the first version, the problem is, well, now I've got to do these joins. That becomes very costly in certain cases. If I want to find things based on one thing, it becomes very costly. Lots of complexity. We have lots of trouble making it scale well. Lots of people do it. The blob model is the problem where now I can't search. If I want to find all cameras that have a digital zoom greater than 8, I can't introspect that blob, right? It's just a blob. So in MongoDB, I can have variable fields such that I can actually store a document with 30 different types of fields that are very different from each other, but still searchable. Probably longer than you were going for.
It's really helpful.
So now we have this database, and it's storing these documents. And we made them JSON-like. It's actually BSON, but they're really mostly like JSON, just more types, binary rather than text. How many here know what JSON is? Okay. Talk about that. Well, and prevent any questions. The reason why it's JSON and not XML is because XML is kind of verbose, and I wouldn't really know technical reason why it couldn't be XML or JSON is like JSON better. So now we have this JSON database, and what do we want it to do, right? We don't want it to be special purpose. Right? We've got distributed key value stores. They work really well for certain use cases. I've got relational databases, that works well for other things. We want a database that actually fills in the gaps. Yeah, it's great. It's great that people no longer fear running multiple types of databases in their systems. But I really dread a world where, in order to build a website, I'm using 15 different data storage systems. I can see a world where I'm using 3. I can see a need for a document database and maybe a couple other things. Right? I can easily imagine where I'm using 3 different databases. I very well want a special database for doing business intelligence or data warehousing or something. Right? There are definitely databases that have very specific purposes, and that's a good thing. Right? That's fine. But I don't want to be running 15 different databases. Right? Like the ops team will just go crazy. It's going to create more bugs. It's going to create more problems. It's going to be harder. So yes, it's good to have choices, but you want to have choices that are general enough that you're not going crazy. So what does that mean for Mongo? Well, what does it mean? That one is we need sophisticated secondary indexes, right? You got to be able to sort. You got to be able to query our things. You got to be able to do unique indexes. You got to be able to do these things in order to have a real database, right? If you don't have unique indexes, how can you use a database for user management where you want to have unique indexes and email address? It's just crazy not to be able to have some enforcement of database level. Dynamic queries, right? I want to be able to go to the shell and just look at my data. I want to poke around. I've got some situation where, hey, I've got some user complaining about this. And well, I just want to go look at the data and see what's going on. Right? I want to go understand if someone did something. I just want to go poke at the data. There's lots of reasons why people just fire up a MySQL shell and just go poke around. So I'm going to do that. That's fine. Sorting, I said, updates, like upserts, right? I want to be able to do things like, hey, I've got a page view counter, just increment this counter, or set this field. I don't want to have to just go shoot my data like a blob and just save and put it. I'll just modify it easily, atomically, right? So if I've got a blog post and I want to say add a comment, I want that to be easy. Add a comment, right? I should say add this comment to this blog post, or increment this page view counter by 1. I don't want to have to say load the document, increment this field, save it, do some sort of optimistic locking or lock the document. I just want to say, hey, increment this counter, and you guys worry about how to make this atomic, how to make this thread safe. Let the database deal with that. Right? Those are the kind of things that we want the database to do. The other thing we care a lot about is we want this to be the primary database continues to things. Right? It's great to be able to have a database for analytics, but also store the data somewhere else, but that's really kind of ugly. Right? It's much easier if you just have a database that you can do all these things with, and that's where your data lives. It really wants to be sort of a place where you can store your data and really be happy that it's going to be there, and that's what the database is doing. Scale, right? So obviously one of the core things we care about early on. So we want to scale linearly, right? Pretty obvious. Scaling algorithmically is not good. You want to scale linearly. The more data you have, you just add more machines. You get 10 times more data, you have 10 times more memory machines, and everything works the same way. We think it's very important to increase capacity with no downtime. Right? Going back to there's no maintenance windows aren't okay anymore. That kind of sucks. The other thing is, when do you want to add capacity? Well, you really tend to want to add capacity when things are going well. If things are going well, the last thing you want to do is take your site down. But if you've got this new site that's going up and it's going viral and things are going great, oh, sorry, we got to go down for 24 hours to add more database capacity. That's kind of a bummer. So you don't want to do that. And scaling should really be, build your application on your laptop. Don't even think about scaling. Now, I'm ready to scale this thing. My ops team goes, adds a lot more servers, and tell the database, hey, go scale yourself. And it does it, right? You shouldn't have to go rewrite your application to scale. The database should handle this for you. Yeah, there might be a few things to consider, but basically, I shouldn't have to do anything. I just want whatever code I wrote on my laptop, signals just my development environment, to work in production at scale. Right? Developers shouldn't have to think about this. 2, we want this thing to be easy to manage and very few knobs. Right? It's great that Oracle has 5,000 configuration options, where if you're an Oracle expert, you can go and tune the hell out of it, and you're going to make it run really fast. It's kind of annoying, though, because if you don't know what those 5,000 configuration options are, you got a lot of trouble. Really want this to be very much start it, run it, you're done. Also, when you're in the cloud, you don't have controls. You want to just adjust, adapt, and be very easy to manage. Right? Very few knobs. The thing about knobs are, it's very easy to add configuration options. And adding configuration options, is always an easy thing to do. Because like, oh, I don't know how to solve this problem. This user wants this, this user wants that. How do I do this? Well, just let them choose. And that's all good and all, except for the fact that every configuration option you add adds complexity, adds more things to do, and most people just want to run with the defaults. They just want to fire the database up and have it work. Right? I don't want to have to go and tune everything to make this thing work. I just want it to work out of the box. And also, we want the thing to be easy to manage and deploy. Right? You should be able to deploy this thing easily. You should be able to manage it easily. It shouldn't be a total headache. The thing you remember with a distributed database is, if you're running a relational database, maybe you have 3 really big sandboxes. With a distributed database, you need to be running hundreds of instances of this. Right? We have a client that has 1,900 Mongo instances. If you're managing 1,900 Mongo instances, you really want to be fine-tuning every single one of them, you'd go completely insane. Right? So if you're running 1,900 of these things, you've got to be pretty careful. So that's the basics of the design goals. Any questions relating to those? Okay. Okay. Can't really read this. So there's some quick terminology, just adjustments, since I get confused sometimes and go back and forth. Databases in a relational database are called databases in Mongo. That's easy. Tables in a relational database. Same concept exists in Mongo. We call them collections. Right? Tables make sense for a relational database because remember, again, it's like Excel. It's like tables, rows and columns. In Mongo, it's a collection. It's more ad hoc. You can put anything you want in there. And then rows in a relational database ends up being like documents in Mongo. Pretty straightforward. So, do a demo. I'm going to do it. We'll do more of a fun demo stuff later. We'll just start with the basics. So, let's say fire up the Mongo shell. You can just go type this in, right? How many people have played with Mongo at all? Like half. I'll go medium speed. Create a JSON document like this. You can just go save it. A few things to note: databases and collections are created on the fly. So if you just go save something to a new collection, it's going to create your collection for you automatically. You can just go save it. Notice you have unlike JSON, there are more types in Mongo BSON than in JSON. So there are date types, there are booleans, there are numbers, there are arrays, there are dictionaries, there are binary fields, there are 3 different types of numbers. I'm blanking on something, but okay. You can query on things. Now let's say I want to find everything written by Eliot. So one is you create an index, and so you can create an index at any field, obviously. You just call it short index. So I'm creating an index on author, and then I'm going to go find every post written by Eliot. Right? And I will return all the posts written by Eliot. You can do, so and someone mentioned this in the Q&A session before, but the query language of Mongo is query by example, right? So you don't say, you're not writing a text. You say, find me documents that look like this, right? That looks like what the author is Eliot. You can also do operators. So instead of saying, find me what the author is Eliot, I can do all sorts of interesting things. So I can do all these list of operators, which I won't list. That gives all kinds of things work. You can do regular expressions natively. You can do all that kind of things. A couple of other interesting things. If you call .find on a Mongo collection, it actually doesn't actually go to the database usually. What it does is it actually creates a cursor that you can do other things with. So you can say .find, that returns a cursor. You can say .count. So you just want to the equivalent of select count star in relational database would just be more like this. You say find everything with the author is Roger and .count. Updates, again, combination of query by example and what's all structured. Looks like a typo on this. Anyone spot the typo? No? Okay. There's supposed to be brackets around there's a missing bracket here and here. Oh well. Update. So this is basically saying update the document where IP equals this and push so this comment under the comments array. There's a comments. This comment is an array. This comment is a new comment that I just defined up here. And basically it's saying that I've got a comments array in my document and I'm going to add this comment to the array. The nice thing is I can do this from lots of different app servers, from lots of different web servers. Mongo will just go ahead and comment in and serialize all these. So you don't have to worry about race conditions. It just adds all these comments onto the array for you automatically. So this is what it would look like at the end, right? So I would go ahead and this is the comment that I just added. And now the document looks like this. Any questions about this so far? Okay. So, sorry. So now, let's say you want to, we already looked at how you would query by author, right? You would just say, find me all documents where author is Roger. But now what if you want to do, find me all blog posts where there's a comment by Fred, right? So this is kind of like my user profile example where I said, find me all users who have an address in New York. Okay? So what you would do is first you create an index. So you create an index on comment.author. Then I can say find. I can say find all blog posts where there is a comment with an author field named Fred. Make sense? Okay. The other thing Mongo does automatically is you've got arrays, right? So now you've got an array here called tags. So I've got two tags on this blog post, tagging databases. And I can index that array, and I can say find me all blog posts where there's a tag called tag. And the interesting thing is when you index an array, it doesn't actually index the entire array, it indexes all the elements of the array itself.
Do you have to ensure indexes?
So the question is, do you have to chart indexes? If you don't chart index, it will just do a table scan, or it will find an index that is close if there are other indexes. So you don't have to, but if you have, it will be slow if you don't. What indexes in Mongo are, they are incredibly similar to the way indexes work in all relational databases. Right? So if you want to do a compound query or a sort, let's say you want to find all blog posts. Let's go back to my example here for a second. Let's say I want to find all blog posts written by Roger, sorted by date. Right? How would you do that in a relational database? You create an index on author, comma, date, and then it would know to use that index. And that's exactly the same way as in Mongo. So indexing in Mongo is really remarkably similar to any relational database. The only difference is that because we have these nested arrays, there are some more things you can do. But all the same rules about indexing in Mongo in relational databases apply exactly the way they do in Mongo.
you would indicate the fact that JSON is the advantage of having real data types, and that's true. But why Mongo is going to enforce when I put in a date that's a date, not instead of just having proper text?
Right, so right now, Mongo has there's no type checking at the database level. So people tend to do that at the application layer with ORMs and those things. I think we're probably going to be adding some sort of validators at the database level too. The feedback we've got from most Mongo users is that they already have validators in all their application layers, and they don't want to have to keep their data in their application layer in sync with their data the data layer. Other people want other things. I think those are very soon. But I think we're going to probably be adding validators in the database side too. Right? There's no reason why you couldn't. You can probably guess what it would look like, but it would basically just be a query document. Right? So the query documents have things like type and exists. Right? So you can very easily imagine where you just say, hey, for this collection, here's a query document that says, hey, age has to be a number between 0 and 120. Hey, there has to be an address in there. Date has to be a date. So I think we're probably going to do that pretty soon. But it's actually, like if you asked me 2.5 years ago, I would have said we're going to have it very soon because everyone's going to want that, and no one ever asked for it. So that's why it's not there yet. But eventually, enough people ask for it, it'll happen. But generally, we had features that people ask for them. When we get enough people asking for features, that it keeps us very busy. So that tends to be how things work.
Does the ensure index, are you running that in line? Like in a relational database, if I was building an index, I would do it long before I ever write my select.
So generally, yes. So generally, you define your indexes beforehand. Most of the drivers have this thing called ensure index, and the idea there is, if you want to just, say, make sure this index exists, do it, and the drivers will cache that information. But most people running Mongo in production will just do the same kind of thing they would do in a relational database. If they want an index, they'll add it. Also, Mongo has a facility for building indexes in the background. So you can say, hey, I've got 5 million things in this collection. It's going to take me 5 minutes to index this thing. I can't go down for 5 minutes. Build this in the background. So generally, if people are going to deploy new code that relies on a new index, before they deploy the code, they'll build their new indexes in the background and then deploy the code.
In this example, you assume that there's a comments index, and you're restricting your data set for find.
So say it again?
You're restricting your data set for the find call to the comments.author index.
So Mongo, so there's a query optimizer inside of Mongo, so it'll look at all the indexes that are there and figure out the best index to use. So if you do a query on comments.author, if there's an index on that, it'll use it. If you look at more complicated queries, there may be multiple choices of indexes you can use, and it'll try to figure out which one to use, or do some heuristics to try. I can talk about that for a long time, but I'm not going to.
Will it use more than one index?
In some cases, they'll use more. We don't really do very good index intersection right now. That's something we're going to be adding pretty soon.
It's like in Oracle and SQL, I can put an index on comments, I can put a separate index on date, and if I query by comment by date, it's smarter than the query analyzer is smart enough to use all the indexes.
Yeah, I basically put them in the bucket of index intersection and sort of merging two indexes. We don't do that very well right now. We'll probably do more of that this year. It will use multiple indexes, like you do like an or an and, it might use multiple indexes. But there are things where we do over index intersection stuff. The canonical example tends to be probably like 50 attributes. I want to put an index on each attribute and say, hey, well, like these 3 attributes equal this, and you can't really have 50 squared indexes. You're just going to build 50 indexes and 2 intersections. So we need to do more in that area. Technically, it's just a matter of getting that code done. So theoretically this year.
Did you talk about Postgres-style expression indexes? Postgres-style expression indexes. So
you mean like filtered indexes?
I mean, like when I build an index on lowercase of something, or on computer shoulders.
A computer index. Yeah. Again, a feature we're probably going to be adding. I'm sure this year or not. So we do some things. We do. So we do this one. We do geo indexes, which basically create geohashes of things and query on those. We have sparse indexes where if a field is missing, we don't put it in the index, so we do those things. They're unique indexes. I think one of the next things we're doing is filtered indexes, where you can say, if this document doesn't match this filter, don't bother indexing this document. So if you've got like expired things, you may not want to delete them, but you may not want them in your index. Computed indexes are definitely something that we're going to do. It's just a matter of getting it done. There was a question over there before.
Is there explain query similar to relational for Mongo?
There is. After you get into the demo, we can do it. But basically, if you instead of .count, you replace .count with .explain. It's the same thing.
If you're assuming the data is changed under here, you're not rebuilding the index.
Indexes are modified, same way the relational databases are. When you insert a document, the indexes get modified. It's all. The index operations are atomic with the write operations to the collections. Right? There's no latency between a write operation and an index change.
How long does a simple index stay in memory?
Sorry?
The simple index that you talked about earlier, how long does it stay in memory or in cache?
So the cache, it's just an LRU cache. So if the index is hot and nothing else is pushing it out, it'll stay in the index forever. If the system is very hot and there's also contention for memory, it's all LRU. Are there role-textual time queries? So there's a query profiler. So basically, you can turn on the query profiler in a few different ways. One way is you can turn on profiling for everything, and then you can see all the operations and how long they take. The other option is you turn it on and say log every query that takes more than X number of milliseconds, and look at those. There's a couple of different facilities for that. All right, one more question on this, and we'll be good.
So you mentioned just 4 unique indexes with Mongo uses the base consistency model and certain number of replicas. Is there a performance penalty to have unique indexes? Does it have to check every node?
What did you say about consistent?
Well, it's base consistent, right? It's not guaranteed consistency across all nodes.
It is guaranteed consistency on primary nodes in a sense.
So it checks all primary nodes.
So you can't do a unique, if you're sharded, if you have multiple primaries in a cluster, you can't do a unique index that isn't based on the shard key. Because that would have to be a two-phase commit. Right? We don't allow things that we require a two-phase commit across the whole system. If we can do a unique index quickly because it's based on the shard key, then we'll allow you to do that. A bunch of updates. Right. So we have geospatial indexes. So if you want to do location search, you can very easily do it. So if location is just an array of 2 values like latitude and longitude, you can just create an index on 2D and then just go ahead and say find everything that's near this latitude and longitude. So if you want to do that kind of stuff, it's pretty straightforward. And this is certainly another example. Documents can get pretty complex. If you look at a lot of example Mongo documents or example applications, the documents get very large and very complicated. But it's pretty interesting. So that's kind of the basics. Any questions on that?
Does Mongo support basic transaction semantics?
So it doesn't support multi-object transactions. So what it supports is basically saying there's a whole bunch of different operators you can do on single documents to do atomic things. Incrementing, yeah. So basically, all of these things you can do atomically, right? So you can do add, there's more, like push, you can add to sets, you can increment, you can decrement, you can do all these things, but all in a single document. Not on, and I think that's something we're trying to figure out exactly how we want to do it. And the reason why we don't allow it today is that whatever we do there, and we are going to do more things, is that we want it to be scalable. And what we don't want to do is have to do transactions that cross multiple servers, because that's what things can get slow. But if you think about it, I don't want to get too much right now, there are many things you can do that are guaranteed to be on a single server that are transactions. So I think there will be a lot more stuff happening there over the next year or so. Yes, so hashes basically, if you look at right, so in here, you've got prime atoms is an array of hashes, basically. So we call hashes basically just subdocuments, right? So address here is basically a hash or whatever, same kind of thing. All right, so let's talk about some of the operational characteristics of Mongo. So one of the base units of the system is something called a replica set. So a replica set is basically the high availability cluster of a few machines. Right, so the simplest version tends to be 3 machines. Sorry, actually, let's go back one step. So what is replication? Why do you care about it, right? Well, I have a single server running Mongo. That for sure, sorry. I've got a single server running Mongo. Now let's say that hard drive dies. Well, my data's gone, my fight's down. That's not very good. So you want to replicate, right? Same thing you do with all relational databases. With MySQL, you set it. You forget how hard it is to set up replication. You want things to, you don't want to have to do anything when it happens, right? You want it to be available all the time. You want it to be able to recover quickly. So what do you really want? Well, you really want to say, I've got 3 servers. All 3 servers should have the same data on all of them, right? I apply something on one machine, it could break somewhere else. If one of them goes down, someone else takes over for it, right? So we call that concept replica sets. Right, so replica sets, because it's a little high availability cluster, right? Typically 3 machines, it could go higher. You can sort of do it 2.5, but really we recommend 3. 3 machines, they all have the same amount of data on them. At any point in time, those 3 machines have elected a primary for that set. That primary is the one who gets all the writes, and by default, all the reads. And so all operations are completely consistent. It's only going to one machine of those 3. If that machine dies, someone else will be, the system will detect that, someone else will get elected, and now someone else will be taking all the rights. Does that sort of make sense? So, little illustration. By default, everything's in there. You can read from the non-primary nodes in the replica sets, or the secondaries. If you read from there, you could be reading stale data. So it's sort of one of these things where, yes, you can do it, but you got to be really careful how you do it. It's very easy to get into a situation where you're reading data that you're not expected to read. So we really don't recommend it unless you actually really know what you're doing, or you really are sure you want to do that. But you can't do it. That machine dies, someone else takes over. When the set goes back online, it now joins the set as a new secondary. Right? So if you need to reboot a box to upgrade the kernel, you just kill Mongo, reboot the box, upgrade it, it'll come back online, rejoin the set as a secondary, and keep going happily. Right?
A couple months ago, Amazon had a network partition problem, which caused, I think it was cascading re-replication of data. If you have like a very large number of nodes in a Mongo setup, would that be susceptible to network partition?
So, all right. So let's take a step back. How would you set up Mongo in the real world? So, there's a few ways you can do it. Let's start with the basics, right? So the most simple way I would do it is if you've got like a single data center that's important, and then you've got a disaster recovery data center in case your primary data center gets hit by a truck. So what do I do? Well, I put 2 nodes in one data center, in my primary data center, and a 3rd node in a disaster recovery data center. Now, if my primary data center gets hit by a truck, I've got a copy of my data. There's a couple of caveats here. Now I've got all my databases and all my application servers in this primary data center. Well, let's say one of those goes down. I don't want to fail over to the one over there because that may be far away. Right? I may put my primary data center in New York and my disaster recovery data center in Chicago in case New York goes away. So what do? Well, there's these things called priorities. So you say, hey, the 2 nodes in New York have a priority of 1, and my node in Chicago has a priority of 0. Well, that means that this guy in Chicago will never be elected primary no matter what. Right? So if the 2 New York ones go away, it will have the data. It will say, hey, I've got the data, but I refuse to become primary unless you actually tell me explicitly to do so. You can tell it explicitly to do so, but it won't by default. So what happens if there's a partition? Let's say that now my New York data center and my Chicago data center can't talk to each other. Well, it's okay, because what happens is whoever has the majority wins. So there's 3 nodes, so majority is 2. So the guys in New York can't see the guy in Chicago, but there's 2 of them, so they can say, hey, I've got 2 nodes, it's fine. One of them will be primary, one will be secondary. That's great. The guy in Chicago will be like, hey, I have no idea what's going on. I'm just going to be quiet, and if you want to read data from me, that's okay, but it doesn't explicitly say you're okay with it, because I have no idea how to sync I am. I have no idea what's going on. There's a lot, you can get this a lot more complicated. We've talked about this for a long time. But the Amazon issue was a little different, and I don't know exactly what happened there.
I think what happened was that their network was bifurcated, and so they tried to find new replica partners, and because all of the nodes had lost, or a significant number of the nodes had lost replica partners, they had a cascading issue where everyone was looking for a new partner at the same time.
Right. So Mongo, so this is where Mongo is. This is where that's left to the operator. Right. So if you lost all of your, if half the machines went down in a replica set, Mongo doesn't know about other machines that can take over. So they don't really have the same kind of automatic re-adding replicas. Right? You have to go and say, hey, that machine's down, replace it with this machine. They're not really the same kind of semantics.
What about what about latency between data centers? Is that gonna? What about latency between data centers? Is that going to cause an issue with
replication?
Yeah.
Up to a point, yes, but in practice, no. We have lots of people who replicate very geographically diverse locations. As long as the pipe is actually big enough to get the data across. So some of the other things about replica sets, right? So you can do some basic things. So you can do the read scaling. You can have deleted slaves. This is a feature that we completely ripped off of Oracle. Right? Lots of things like this. This is an example of Oracle DBAs asked us for this. We're like, okay. The simple idea here is I want to have, I've got my 300 replica set. I want a 4th node that is always running exactly 2 hours behind, so that if someone goes and fact figures my primary and drops a collection, well, this guy, if someone notices within 2 hours, this guy's never going to apply that, so you can kind of take over and recover from that easily. You can do different priorities. So you can do 1 and 0, like I said before. You can also do more interesting things, whereas you've got some big boxes, some medium boxes, some small boxes. You can prioritize which boxes are primary and things like that. One of the other things you can do, and this is basically something called replication acknowledgement. And we call it a few different things in a few different places. But the basic idea is that you do a write, by default, it's going to go to the primary. It always goes to the primary. The question is, when do you acknowledge that write to a user? Right? So it's one thing to say, hey, I sent it on the wire, we're called to get to the database. That's great for maybe you're counting page use, that's fine. Another option is, hey, once that thing gets written in memory at the primary, I'm okay acknowledging to the user. Some writes, that's okay. For some people, you want to say, hey, if this writes on disk on the primary, that's good enough for me. For a lot of people, though, they don't actually trust any one machine. So what they really want to say is, I don't care for disk. What I really care about is that I want this to be in memory on 2 machines before I tell the user. And for some people, and for certain kinds of writes, maybe user registration, hey, I don't want to acknowledge this write to the user until this write is in memory in 2 different data centers, 2 different racks, 2 different power units, whatever it is. And so in 2.0, I should have said it can be 2.0, not coming to 2.0, 2.0 came out 5 months ago. Just back a little. You can do things that say like, okay, don't tell me this write has succeeded until it's in 2 different data centers. So that's kind of nice because, and you can control this per write. So on the same collection, right, let's say you've got blog posts. Well, if I add a new blog post, I may really not want to lose that because if I just spent an hour writing because I don't want to lose it, that would kind of suck. So I don't want to acknowledge that until it's in 2 different data centers. Now let's say the other extreme is page view counters. Just fire that. If I lose a page view count, I really don't care too much. And there are things in the middle. Like what about adding a comment?
well, I don't want to lose a comment, but I don't need to wait for it to be in multiple data centers. So once it's on 2 machines, say that that comment has been successfully written. And the nice thing is you can actually tune that for every single write you do. So you can sort of do as you please. And this is an area where there is a lot of value in very fine-tuned user control, because writes are very different based on what they're doing. And it doesn't make a whole lot of sense to make page counters slow to make sure they're guaranteed to be safe, but it makes a lot of sense to say, hey, I just registered a new user. I really, really don't want to lose that, no matter what. Right? Even if the machine that I'm writing to is completely blown up, I want to know. Right? Even if this data center gets hit by a truck at the next 300 milliseconds, I want to know. So those are kind of some of the things that you can do with that. Any questions on replica sets? Any more questions?
Does the replica set support the rewrite colons similar to RIAC? So for example, you say I want to write to only, so when you talk about replica set, right? So each node have exactly the same copy of data, correct?
Right.
Unless you shard the data, you're not going to have.
Sharding is different. So
okay.
Every node has the same data with some delay. Okay, moving on. So this is great. So now we've got most of the features we want. We've got data durability. We've got high availability, but we're still not scaled at all, right? Yeah, we can do a little bit of read scaling with read from secondaries, but that's sort of eventually consistent. You really don't want that, so it's kind of crappy. So you really don't have to scale. So what do? Well, then comes sharding. The sharding basically is built on top of replica sets. There's a lot of misconceptions in the universe, mostly spread by other people, that say that because sharding is built on top of replica sets, it was designed later. It's all kind of a myth. It was all designed at the same time, just built that way, because you got the building blocks before you can build the building. But the basic idea is, what is sharding, right? So you've got this replica set, so why do you want to shard it? Well, the first thing is you want to distribute write load. If I need to do 1 million inserts per second, I can't do that on a single box no matter what, right? It's too many, can't do it. I need to have 2 terabytes of RAM in order to keep a working set in RAM, right? I don't want to spend $5 million on a massive SUN box with 2 terabytes of RAM in a single box. So I need to distribute the RAM. I want to do consistent, I have to have consistent reads, I just have to, and I need to do 5 million of them per second. Well, you can't do 5 million reads in a single box, I got to distribute those reads. And, well, you want to preserve functionality. So how do you do that? So what Mongo sharding does is it automatically takes your collections and spreads them out across different replica sets. So there's a few things that are really important to know first. So first of all, sharding is range-based in Mongo. Range-based sharding means that if I'm sharding my user profiles collection, I pick a shard key. Let's say I pick a shard, say I want to shard my email address. So that means that the whole user space is split up into chunks. So every user whose email address starts with A goes to one server, B goes to another server, C goes to another server, and so on and so forth. If I want to find the user who starts with E, I know exactly where to go, because I've basically got a phone book that says, hey, for all email addresses that start with E, go here. If I want to do a query for state, what it does is basically a distributed merge sort and parallels the query and does a distributed merge sort out of it. What sharding will do is, let's say you go ahead and add a new server. Right? So you started with 3 shards in your cluster. You add a 4th one. What the system will do is it will take some of those chunks and move them around. So this is sort of the big complicated diagram. Right, so this is basically what a shard. These are all the components of a sharding system. Right? So you've got shards. The shards are where the data lives, and a shard, in most cases, is a replica set. Right? So you've got 3 replica sets here, and each replica set has 3 nodes. Right? So each one of these vertical boxes is one replica set, and they all have the same data. The 3 going across are the 3 different partitions. So each one of those partitions has 1/3 of my data. On the left, you've got config servers. Config servers just store the metadata about the system. You know, where the chunks live, where the shards are, all that kind of metadata information. And you've got these MongoOS processes here which basically are routers and load balancers. The whole system kind of is built on top of this. So I'm not going to go into too much detail. Let's just go through a few use cases, some of the more interesting ones. So how many people here know what twitpic.com is? So let's say you want to build a photo sharing site for Twitter. Right? The idea is people take a picture, they put it on the internet, and they show it to their friends, and it's a picture of some cat or something. So what do you care about, right? So one is you want to be able to upload lots of images at the same time, and you have to read lots of images, because something goes out on Twitter, I'm going to get lots and lots of reads for this. I've got a lot of data over time, so I need to scale that. But in reality, 99% of the data people are actually looking at has been written in the last 2 months. Does that all kind of make sense? So the first question is, or really the big question is, how do I do this in volume? So let's start with the basics. So one is, these images are not going to be huge. Right? They're all, let's say they're going to be less than a megabyte. So the nice thing in Mongo is you can store binary data right in a document. So the first thing I do, I'll make my document look kind of like this. Right? I have a photo ID and a binary blob that represents the data. And then just go shove that in the database. So that's good. So the real question is, what is my photo ID? And when you think about that question, the real answer is, well, what is my URL? But the URL is going to be, picturething.com, or twitpic.com/something. And that something is going to be the image ID. So really the question is, how do you define that image ID, and then how do you shard it? Well, ideally, you'd shard by that image ID. You're always querying the image ID. Right? There's always going to be, hey, I've got this image thing, go find it for me. So now the question is going to be, what do I do? How do I define that? So the answer in MySQL is always auto-increment. Right? Define an auto-increment key for the primary index, and every image gets just one higher than the next. So how many people? So if you do auto-increment keys, there's a few good things about that. One is that every image's key is bigger than the next one. So if, how many people here know what a B tree is? Enough. So a B tree, basically, it's a tree-based index, right? If you're always putting in keys that are bigger than the previous ones, it always goes to one side of the index, meaning that you only have to keep one side of the index at random. So that's really nice, because now if I've been around for 20 years, I only have to keep the last 2 months of data, 2 months of index data at random, not the entire index at random. The problem with sharding on an auto-increment field is, remember, shard keys are range-based. So So when I was saying shards, range-based shard keys before. Better. So it kind of looks like this. Right? Let's say I'm sharding by email address, and I basically have these ranges. Right? So I've got a range from A to F, and that goes to shard 1. A range from F to M, that goes to shard 1, 2. Range from M to R, that goes to shard 2. Range RZ, that goes to shard 3. Now let's say instead of using letters, I'm using numbers. So at some point, I've got a chunk that says, hey, from 1 to 100 goes here, 100 to 200 goes here, 200 to 300 goes here. I've always got some case where I've got 300 to infinity. Right? So I've got to have some mythical max value because every key has to have a location. So I've always got one chunk that is some number to infinity. Now, if I'm using an auto-increment key, that means that every time I introduce a document, it's always going to that same chunk. So what the system's going to do is it's going to keep splitting it. It's going to keep taking that chunk from 1,000 to infinity, and then it's going to split it and say, hey, it's too big now. Now I'm going to make 2 chunks out of it and make that from 1,000 to 2,000 and 2,000 to infinity. And it's going to keep doing that over and over and over again, which is fine. It will take those chunks, and then we'll have one shard with 10 chunks and one shard with no chunks. So then I'll say, well, that's not good. And then it'll move some of those chunks around. But what have you done now is now you've got one shard that all the writes are going to one shard because they're all going to one chunk. And not only does that one shard do all the writes, but all the reads are coming from there too, because, well, all the reads are from stuff you just posted. And what's worse is not only does that shard take all the reads and all the writes, but it also has to have extra capacity to move data from itself somewhere else, right? Because eventually the goal is to get the data off, so it distributes it. But in order to do that, it's actually got to do some work, right? It's not just free. It's got to actually use some CPU, use some network, use some disk, and actually do this work with it. So it's actually, kind of that. So, sorry. I just heard though she was a pro name, so we'll see how that goes. So auto-increment keys aren't good. They're good because they're good for working set size, bad for sharding. Now let's say we just hash the data. Purely random hash values, right? You can do consistent hashing, we don't have to hash anyone. Just take the values, hash them. Well, the problem now is, well, what's the good thing? The good thing is now my writes are completely evenly distributed. My hash key's any good, all my writes get evenly distributed, my reads get evenly distributed, these things are evenly distributed. I've got lots of chunks, but I never have to move them around. But if I start out with 5 chunks in each shard, and then I end up with 50 chunks in each shard, they're all going to grow at the same rate. So I never have to move any data around unless I want to actually add capacity. That's really nice. But now let's go back to the other problem with the indexes. So I've got a hash key, it's a random access index. So I need to keep the entire index in RAM in order to keep it fast. So if my site's been open for 20 years, I've got to have my entire index sitting in RAM. That's kind of unfortunate, and it's really not great. Now, Mongo will happily do that for you if you have enough RAM. It just means you have to have more RAM. I'm going to skip the third one because that one's kind of boring, and go to the fourth one. So let's say you do something a little bit more interesting. So what do we care about? One is we want to distribute writes, we want to distribute reads, and we want to prevent as many migrations as possible. This because that creates more work for the system. And we also want to have these indexes that are right balanced, so that our working set is small. What you can do is you can make this interesting key. So you make your URL to twitpic.com/2011 dash, or 2012 now. twitpic.com/2012 -01, and then some hash value, some totally random value. All right. So what does happen? Well, assuming you have any load at all, in a single month, you'll have lots of chunks. So you'll have chunks that look something like 2012-01 A to B, C to D. So maybe you'll have 1,000 chunks that all are prefixed with 2012-01. Those chunks are now going to get distributed. So I'm going to get a good write distribution because I've got enough chunks sitting in that same month. But when I'm my working set size, all of my data lives in either 2012-01 or maybe 2011-12, where the month rolls over, or in a really extreme situation, maybe 2011-11. But I only have to keep 2, maybe 3 months of index data around. So if it's 20 years from now, my data set still, my working set size is still pretty small. Now occasionally you have to go load something up that's really old, that's fine, but for the most part, 99.9% of your reads are coming from data right in the last 2 months. Your working set stays small, things stay fast, and cheap to run. Any questions on it?
If you're building the MD5 against the data, then in order to retrieve that, you'd have to have access to the data in order to compute the MD5 in order to
put the
retrieve
MD5
it.
in the URL. So the URL becomes twitpic.com/2011-12- whatever the MD5 value is.
So after it's computed the first time, it's returned to the user for...
So when a user uploads the image, you can pick the hash, you store them in the database, you give them the URL, and says, hey, your URL is this, and that URL contains the hash.
Well, why not either MD5 the photo ID, or even simpler, just take the last character of the photo ID and use that as your key?
Well, we're trying to figure out what the photo ID is. We don't have a photo ID yet.
I thought it was an auto, it was an incremental.
No, I'm saying that's one option. I'm saying,
if it was incremental numbering and you want to do 9 shards, just take the last digit.
well, you could just take the, if you had an additional auto increment number, you could take that and hash that. You can take any unique value for that image and hash it. You just hit something, right? MD5 for the date is fine, and check some of the whatever you want to do. It doesn't really matter actually. As long as there's some unique identifier for that image, it really can't be anything. I just like MD5 for the data because then it's guaranteed to be unique and simple. And
Yeah, but there's a cost to MD5, especially if your data's big.
yeah, but MD5 of a 4 meg image takes, a few milliseconds, pretty fast. And you only do it once. But yeah, and a lot of things do it anyway for validation. So a lot of people do that anyway. There's MD5 on the client and MD5 on the server or something like that.
Would you need to expand to a third attribute of the actual key itself?
If you're worried about MD5 collisions on your images, yes. Or MD5 collisions on the same month, the date. If you have trillions of images being uploaded, it could become a problem. But it can be any unique identifier you want. Any other questions on
But say if you're actually starting with month, and most of the data is coming in for the current month, aren't you still sending most writes to the same nodes?
Right, so what happens is for the first hour, all the writes go one place, and then it quickly distributes out.
But it's sort of month. I don't understand why would all writes the same month be on the same node? How does it distribute out?
Because there's many chunks per month. So let's say you start out from scratch. So you've got a single chunk. The single chunk is negative infinity to positive infinity. You start inserting some data. Well, now it's going to say, all right, so what will actually do the minimum value. So now you've got a chunk that goes from negative infinity to 2012-01-C. And then another chunk and then another chunk, the chunk from 2012-01 to C to positive infinity. Then that one gets split. So you end up with a chunk that's 2012 C to F. Now you keep inserting data into that chunk. I'm going to type this. So, actually, this is pretty good. All right, I can use this. So, you start out with, you're in the negative infinity, positive infinity for a second. Because it doesn't matter. So you start out with A to Z, right? So then you go to A to G and G to Z. Sorry. That was right before. So, you start out with this. You start out with one chunk with this range. You keep inserting data. So what happens? Well, then you end up with a chunk with so this goes away. So you split this, and so now you have this. Right? So you do this. So then you're going to keep having more and more of these. So now you're going to go to F. F to M. And so you keep, so chunks are 64 megabytes. So if you're inserting thousands of images, you're going to have lots and lots of chunks that do this. And what you're going to have here is you're really going to have a chunk that's like Y. Something like this. Now the first time you insert an image for February, it's going to go into this final chunk. Right? Now as soon as you start inserting a few, as soon as you do that, it's going to split it up. So now it's going to end up looking like this. Right, so now you're inserting data. So 1/26 of your data is going to go here, or is going to go here. 25/26 is going to go here. Now this chunk is going to start getting split again very quickly, because you're inserting a lot of data quickly, and then those chunks are going to spread out, and so the data ends up very well distributed. can actually, like, if you simulate this, it kind of is obvious how it happens, but so it actually is distributed quite well, very quickly. And there was a cheat too. If you want to preempt, you can also cheat, and if you want to just go ahead and create some artificial splits ahead of time to make it a little bit smoother. But there's lots of ways to cheat to make it nicer. But it all ends up being the same in the end.
And what do you need to define in advance? Do you need to define the number of shards in advance? Because you mentioned that splitting is automatically.
No, so all you define in advance is the shard key. So you say, we can just do this. If you have time, we'll do it. Basically, you say, I want to shard this collection. I want to shard it on email address. At that point, there are some number of shards. It can't be anything. It could be anything. And what happens is, and you can add shards whenever you want. But when you add shards, okay, so let's assume that at time 3, you only have a single shard. Then at time 4, you add another shard, and so what it does is it just starts moving chunks. And it'll keep moving chunks until all the shards have the same number of chunks. So if you start with 3 shards, each one of them having 100 chunks, you got a 4th shard. What happens is all the chunks at the end end up having, so 75 chunks. All right, just to finish off. There's a lot of people using Mongo. This list is almost a year old, so there's a lot. And there's other use cases too. All right, any questions?
How does Mongo know when to split the chunk?
So it keeps track of how much data you're inserting to a chunk, and then we'll check to see if it's big enough to split it. So it's basically monitoring, and as you're modifying the data in the chunk, it keeps track of how big your chunk is. And when it gets 64 megabytes or 100,000 documents, it'll split it.
Before we go on to Q&A, I just want to take a 2-minute pause. First off, I want to thank all of our sponsors for this wonderful database month event, Continuing Scale-Based Schooner Information Technology, and of course the awesome Pivotal Labs that's supplying this incredible space. I want to thank our speaker, Eliot, right here, CTO of Tengen. Let's do QA. Questions? You had your hand up, right?
Is there like open use on the street, like a state, let's say we have users from different states, as a shard key, you're always guaranteed like certain letters and such. And New York. Is that a better alternative to maybe, start hashing separate keys?
So what do you want on a shard key? So one is you want good right distribution. That's a key thing. 2 is you want enough granularity such that there's always enough chunks, right? So you don't want that situation where there's more than a chunk's worth of data for a single shard key, because then you can't chop it up anymore. So state alone isn't good enough. I mean, you have a tiny bit of data, like fine. But if you have users, you may have millions of users in New York, so you don't want to do that. 2 is, queries by shard key are going to be simpler than queries by not shard key. So generally, if you have users, the most common method is by email address, probably will shard by email address. You don't have to, but it's probably good. The other nice thing is you want a little bit of isolation is good. Right, let's say you have 1,000 shards, like 3,000 nodes in your system. Well, the odds of any shard having some problem is non-zero because you've got so many, something bound to go on somewhere. So if you could do a little bit of isolation, so that if you shard all of your collections by email address, then you know that we're going to do some more feature because they'll keep data for all email addresses on all collections in the same place, so that if you lose one shard, you don't lose all. You don't go down completely. You just lose 1/1000th of your users have no problem. So there's some nice things that we mentioned.
Right there in the back.
Do you recommend to have, what about the hardware for nodes? Is it better to have homogeneous nodes, or does it really matter as far as the replica sets?
It's always better to be homogeneous, but in reality, no one ever is. So the system works fine without it.
What about the power of the box? Is it better to have more powerful boxes versus,
we have this law. The question basically is, should you have the question is often asked, should I have lots of small boxes or fewer big boxes? And what I tell people is find the price performance break in the curve. Right, it tends to be around 10 to 12. Whatever box tends to cost $10,000 or $12,000 for buying hardware tends to be where that price performance curve is right. Buy that. Don't worry about how big it is. Figure out what you're going to get the most bang for your buck. Buying hardware, buy those boxes. You don't want lots of small boxes because that's just more maintenance, more boxes, more those features. But wherever that inflection point of the curve is, in my experience, it's around $10,000 to $12,000.
I actually have a question about the document structure. Even though it's the Mongo and multi-document databases don't have relations at all, they efficiently handle one-to-one and multi-end relations. But what I wonder is how they handle the end-to-end relations. For instance, think about a product catalog, right? And how do you store data like customers who will be with this item also will be with that item?
True is how you do managing Kubernetes join. Yeah. And really what it comes down to is you need to do a client side. You need to do a client on the client. Right? So you say, I know Bob, here's Bob, here's all the products that Bob looked at. Find people who looked at these products also. So instead of doing one query, you're doing two queries. Or in some cases you might do 3 or 4 queries. And the better, and you can say that doing that in SQL is a little bit simpler. The problem with scaling that is hard, right? So you're basically pushing a little bit of work to the client side in order to scale and make it easier for other guys. Right here.
What situations, if any, would you see using other NoSQL solutions besides MongoDB?
There's a lot of them, so I'm not going to go through all of them. But so let's pick some of my favorites. So CouchDB. In my opinion, the best feature of CouchDB is online-offline syncing. So if you want to build something like Lotus Notes, where you actually have like an offline desktop application that should sync with other desktops, that works really good. That's very great for that. All the Dynamo databases are great if you care about if you want to distribute a key value store where you're okay with eventually consistent. Something like that. How do people know what I mean by an eventually consistent data store? What that actually means. So, I don't want to go into it too much, but there's a lot of caveats about how you use them and what you can use them for. But if you're okay with those caveats, then the trade-offs are good. Those are the two types that, in my opinion, are useful in certain many cases. Okay, right there in the back.
Do you provide enterprise level support, 24/7 support or something like that?
Enterprise what?
Enterprise level support?
Yeah, Tendon provides commercial support for
Next question.
How does Mongo use MapReduce?
How does Mongo use MapReduce? So people use MapReduce in Mongo. Mongo hasn't built in MapReduce. It's JavaScript. It's not amazing. It's one of our least favorite features. People use it for aggregation. It's annoying to write MapReduce for simple aggregation, but in SQL you can do very simple things like select state, count state, group by state. That gives me the state and how many people are in each state. It's really simple. Doing a MapReduce in JavaScript is really great. So we're not deprecating MapReduce, but we are adding a 2.2. You can play with it now. If the blog goes about it today, actually. There's a whole new aggregation framework for letting you do simple aggregations like that, or actually pretty complex things, without using MapReduce. The MapReduce is nice with a big hammer to do lots of things with it, but it's also very heavy-handed and right? It's actually running code in the database rather than running a declarative thing that's in a hand. This is what I want to do.
Next question.
So if you support transactional consistency within documents, not across documents, can you support things like deduct a certain amount from this one ID and add it to the other ID in a consistent state? So I can't have two people running the same transaction at the same time and over-transfer funds from one account to another account. Within the same document.
Within the same document, yes. Not across documents.
Is there any locking or locking? How do you prevent other, say, web services from making the same conflicting transaction?
It'll basically serialize it in the database. So it's basically locking it. It's doing locking itself in the database layer.
Sure. Last question?
Yes, backup restore.
There are lots of ways to do backup and restore. There's pretty well documented on the website, so I'm not going to go into too much, but there are lots of ways to do it. Various ways.
Okay, that's a short answer. We can do another question. You had your hand up right there.
Is there any plan in the future to support full text search with invert index? Full text search with reverse
Yeah,
index?
there's a most NASCAR feature. There are plans to do it. We'll not make any guarantees as to it.
I want to thank everyone for coming, and I want to thank everyone, our awesome speaker, Eliot Horowitz, CTO and co-founder of 10Gen. Show of hands, who here uses GUI tool, Mongo? Any form of GUI tool? Now, we can't be the only one person who doesn't do this on his hand. You win? All right. What's yours? What GUI tool? Which GUI tool? What's it called? I can get a little here. I see a hand up.
It's JMongo browser.
Which one?
JMongo browser.
JMongo browser?
Yeah, it's a Java tool.
Okay. Anybody else?
Notebook?
Asking you so.
Thank you.
All right, let's do more books. All right, so the MongoDB GUI. So no one's using the GUI. Everyone does this for the command line for what? Let's start with a backup question. How many people use Mongo here? Okay, that explains it. About half of you audience. Okay, so half of you haven't used it yet. Okay. Let's do a Mongo question. What kind of non-relational database is Mongo by definition? What do you store?
BSON data.
All right, well, that's like everyone. Now we're going to move to.
BSON data.
What is it?
BSON.
BSON data. That's a better definition than documents. So we get another book. All right. Someone throw out a question. It's easiest that way. Give me a good question for Mongo.
Why use Mongo?
Why what?
Why do you use Mongo?
Why do you use Mongo? That's like a really subjective question, but that's actually not bad. What's a good use case for Mongo over a relational database?
It's free.
Nah, that's like all databases. Very flexible. People can say that about all open source databases. You can change your schema online. Schemaless. But you got a book already, right? No, I didn't get it. I had these cards. Let's do that. I like this. Let's do another one. What other reason to use MongoDB over other databases? What's going to get a body like that? No, but economies of scale, that's actually also subjective. Like the other databases, you're trying to claim that. Whether they're right or wrong is a different story. They're all kind of claims. You got your hand up, so.
No joins.
No joins. Is that a feature or a bug? First of all, you kind of do have joins because you have what we call it, the linked records. I think it's the official term for that. So it's a hack. Yes? That was said. Every database goes separate registers. Yes? That's good. Why? Keep it up now.
You add another server to the replica set and just
Good. Right. More books. All right. Other benefits of MongoDB over other databases. Other databases do that. Questionably, they do. So hand up. No. There you go.
Cluster setups are supported.
Cluster setups supported, but that's not unique. That is true. That is a benefit, but it's not unique. Yes.
Support ad hoc query.
I don't know. Is that a benefit? What did he say? Supporting ad hoc query.
Is that it? MapReduce?
Since I don't know, you get a book. You stumped me.
Thanks.
MapReduce, maybe?
You get the other. You get another book. That MapReduce is what I was waiting to hear, man.
Okay. I didn't think MapReduce was unique.
The MapReduce is definitely get a book. That is one of the awesome things of MongoDB. All right, we got more books. Not many more. I don't think we'll start the presentation soon. More benefits of MongoDB. Wow, there's hands all the way over there. Yes. Location data?
Geospatial data.
Geospatial data. If you can name the one other database that has built-in indexes for geospatial data, you get the book. There's only 2 agreements. Couch is wrong. PostGIS is right. You get it.
My eyesight doesn't have geospatial.
How many books? Oh, not many. Last 3 books, last 3 features. Yes? Redefine. There you go. Stores an object. As you put it in, it comes back out. Arrays, objects, whatever. More. Hand up. Sharding. Sharding! Yeah, now where was that? Wait for that. That's a major aspect of MongoDB. Cool. Okay. One more. Yes. Indexes on non-key values. Secondary indexes. Most of the NoSQL storage don't do that. That is correct, but like every relational database does.
Because 10gen goes down to 32, make it easy to start using auto.
10gen is totally awesome, but that doesn't lie. Oh, come on. Anyone else? Last book?
No fixed schemas.
No fixed schemas? Fixed schemas. That was kind of said in a different way before. Sorry. Okay. Anybody else? Yes? Well, you're really close. Real-time statistics, it does do really well, high-write data. However, like, there's some type in the market that is questionable if it's unique. Yeah.
Document-based query language.
That's it, man. You got it. Document-based query language. That's a good one. All right. Document-based query language. Well, the book is like a primer on MongoDB.
It's also available on GitHub. You just search the name.
Hey, you know what? We got one more. We got a bag. We'll do one more. We'll do one more. It's a cool bag. It's green. Wait, can I give away your bag? All right, bag. Name another feature of MongoDB. You got one already.
No, I didn't.
You did?
No.
You sure?
Let's see.
Okay, what is it?
Journaling.
Journaling. What do you
Yeah.
think? Journaling? Is it unique to MongoDB? No. Okay. Sorry, CTO says no. Yes. What? Gridfest. Nice one. Get it back.